Okay, so in today's lecture, I'll basically spend quite some time going over the Kruskal coordinates again and explaining what they teach us. So last time we wrote them down. So let's remember everything we've done from the beginning. Let me summarize the coordinates we have been using. So here we have T, R, theta, phi, then Eddington-Finkelstein, we have two choices, V R theta phi or U R theta phi, and let's label what we can study with this. Exterior, though in principle we could study the interior, but we can't connect them. Here we can study exterior and black hole interior. Here we can study exterior and white hole interior. I didn't do it. I would urge you to check my statement that these ingoing coordinates allow me to study the black hole interior and the outgoing coordinates allow me to study the white hole interior. You should also be able to prove theorems. So we proved one about this case using these, that no causal curve in that interior can come out. You should prove that in these coordinates no causal curve from outside can go in. Last time the derivation I gave of that thing was a little bit hasty and not hasty, but it was a little complicated because it is. But I found a slightly more streamlined way to write it, and I've put that into the notes. So you'll be able to see that. And then finally, we did Kruskal, which are great because, so these are U, V, theta, phi. So as you can see, we are actually not doing anything to the angles. We are doing it only to the first two coordinates. And there are many good things about this, and I'll spend a lot of time discussing them now. But the first thing to say is that we can study the exterior, which is called region 1. I'll draw it in a moment. Black hole interior, region 2, white hole, region 3, and a very weird region called region 4, which nobody really asked for, but it somehow came out. And this is a maximal extension of the Schwarzschild space-time, so there can't be any more regions than these four. And the fact that, so let's draw them. So this is the V-axis, this is the U-axis. Obviously this is 0, this is region 1, 2, 3, and 4. And good. Then we can label a few things. This is the future event horizon. Well, let's derive them. For that, let's remember what is the metric and what were the coordinate transformations. I'm just reviewing everything because there are so many things we did that it's very easy to forget them. So we always start with T and R. From here, we define R star, which is a function only of R. From here, we define V to be T plus R star. That makes it, is that right? I think this is correct. And U, so actually we define V or U. We found that using both U and V is okay, but it's not really effective for the reason, okay, first let's notice what it is about these. So V equals constant is R star equals minus well, r star equals minus t, or t equals minus r star. So as t increases, r star has to decrease. And this is outgoing because then t is equal to r star plus a constant, so they increase together. And so here's a confusing thing. If I am in this coordinate system, then everything is perfectly smooth across the horizon, and so V is well defined outside, inside, and on the event horizon. It's also true if I'm in this coordinate, but not V. In that case, U is smooth outside, inside, but this horizon is a different one. It's the past event horizon, but U is smooth everywhere. Now supposing I take both U and V to be coordinates, I could also, notice that it's nowhere in my list to take U, V, theta, phi. That is small u and small v rather than capital. That's not in my list. Here we encounter the weird thing that we have to decide which of u or v or is smooth at r equals 2gm, but we can't take both to be smooth. Let's see why. I said it briefly last time, but let's just see. So what happens is that at r equals 2gm, we know that r star goes to minus infinity. Okay, so the only way v can be finite is if t goes to plus infinity, far in the future. The Schwarzschild time goes far in the future. But if t is plus infinity and r is minus infinity, then u is infinite. So it's not smooth at r equals 2gm. I could make it smooth by saying, well, when r star goes to minus infinity, I'll send t to minus infinity in such a way that this combination is finite. But now both of these are minus infinity, v is infinite, and so v is not smooth across the horizon. So only one of them can be smooth across the horizon. And depending which one you pick, you will enter the black hole or white hole. So actually, at least that is there, because with u and v, you get that feeling of symmetry. You feel that somehow ingoing, outgoing are both there, so somehow both horizons should be there, the future and the past. But they are there in a rather subtle way, which is that we have to decide which one we keep fixed on the horizon, and then we enter one or other of the interiors. So that's why small u and small v has somewhat limited use, and it's rarely even written down. Usually it's a very quick passing step, going from Eddington-Finkelstein through this to capital U and V. And capital U is equal to minus e to the minus small u over 4gm, and capital V is equal. So now we are going to do capital U. I hope my notation is clear, the difference between small uv and capital UV. So this is e to the v by 4gm. And now the diagram we can draw, we've drawn that diagram. But what happens is that with this change of variables, we only do it outside in the exterior, which is unique. There is a unique exterior to start with, region 1. So that's this region, and we make this change of variables only there to capital U. And just inspecting these, small u and v can take any value from minus to plus infinity, and therefore capital U, because of this minus sign, can go up to minus infinity, and then it can only go up to 0, because, so if this goes to minus infinity, then we get here, and if it goes to plus infinity, then u terminates at 0. And since both those ends are not really there, they are limits of small u, so these inequalities are strict. And v, on the other hand, is manifestly positive and ranges in this range. So by this we get region 1, which we can clearly see on the diagram. is V positive, U negative bounded by that. So that is comfortable. And we, as I said last time, we extend to both of them, taking any value from minus to plus infinity. There are three cases apart from this one, and they give me regions 2, 3, 4 in ways which you can very easily work out. What's the metric? It is minus 32 gm cubed over r. And what's happened here is that, and then there's e to the minus r over 2 gm and du dv plus r uv d omega 2 squared. And notice that this factor has dimensions, so c is 1, everything else is visible. This has dimensions of length squared, and that's because capital U and capital V are dimensionless, unlike small u and v, which had dimensions of length, which they inherited from the beginning. Okay. Now let's talk about horizon. Okay, now the point is that this R is very complicated, so this is really not the best metric in which to actually compute trajectories. Okay. There is a formula which will tell me how to find R, and it is UV product is equal to minus R by 2 gm minus 1 e to the R over 2 gm. And if I want to find R, then I have to invert this function, which you can do, I'm sure, in terms of, is it this Lambert function or something? Yeah, there's some function, but okay, it's a complicated function, but in principle it's doable for sure. Okay, now let's ask how we approach the horizons. So we see that R going to 2 gm, of course, must take us to a horizon. That's what we expect, but which one? Now it actually matters from which side I'm taking R. Well, first of all, good. First let me say something. So this implies UV equals 0, which implies U equals 0 or V equals 0. So here we don't have the complication of the small UV coordinates that we had to make a decision how we are going to go through a horizon. We simply note that the horizon condition is this, but it's a pair of straight lines as per this, and those are not really straight lines, they are actually null hypersurfaces, each of them. So let's be clear about that. U equals 0 or V equals 0, each is a null hypersurface. So for example, the coordinates, let's write it here. So here the coordinates are V, theta and phi. On U equals 0, the independent coordinates are V, theta and phi, and that has signature. So this is a space-like sphere, and this is null, so the whole thing is a null hypersurface. And on this one, it is, the coordinates are U, theta and phi, so in both cases null hypersurface. Now in these coordinates, it's not that the size of the sphere is constant, I think, because everywhere, because R depends on U and V, so the size of the sphere will vary. But as long we are only interested to know if it's 0 or non-zero. If it's non-zero, then it's an actual sphere. If it shrinks to a point, something weird can happen and we should worry about it. Okay, good. Now this is one set of observations. Then we also find it convenient to define capital P equals U plus V over 2 and capital R equals U minus V over 2. And they are nothing but the horizontal and vertical axes of that diagram which disappear. So this is R and this is T and this is V and this is U. But now something really nice has happened. We have a maximally extended space-time and U and V are null, and that means that the light cones are all, so the null directions are at 45 degrees, and so the light cones everywhere look exactly like this one. So if I'm at this point, the light cone will look like that. If I'm at this point, the light cone will still look like that, wherever I am in this entire diagram. And in fact, we can draw both sides of the light cone if we want. They don't tip or turn over or face some other way or anything. The nice thing that has happened instead is that the singularity has gone here. So now something does change, which is the nature of the killing vector, but I haven't said anything about killing vectors till now. Okay, so the light cones simply point in the same way throughout, and T is always the direction to the future. This also shows that the space is time orientable, as I already have argued, but in these coordinates you can just see it from a diagram. If there's a light cone which is really the same everywhere, that's the simplest way of saying that the space is time oriented. Space-time is time oriented. Okay. Now, what about infinity? Well, if I go out here, I go to infinity. If I go out here, I go to infinity. These are regions 1 and 4. And one thing you see is that each of them is an asymptotically flat region with its infinity everywhere up and there. Okay. In the Penrose diagram, we get a scry coming here and bounding it. So each of them looks perfectly like its own space-time. Okay. So 1 and 4 are distinct and individually asymptotically flat regions. However, 2 and 3 contain the singularity and they end there. So once you have the singularity, it's some curve in these coordinates actually, that's the end of it. Okay, so let's look at the singularity. So for the singularity, we have to take that formula and for UV and put R to 0, so that we find out what curve gives me the singularity. If I put R to 0, then UV becomes 1. Okay, and UV equals 1 is a hyperbola with 2 branches, and one branch is this and the other branch is this. And so one is the black hole singularity and the other is the white hole singularity. So, and R going to 0 is in regions 2 and 3. R can't go to 0 in regions 1 and 4. Because R will have to cross 2 GM and regions 1 and 4 are bounded by horizons. So R going to 0, which implies UV equals 1. So this has a branch U greater than 0, V greater than 0, which is in region 2, and it's the black hole singularity, and a branch U less than 0, V less than 0, which is in region 3, and it's the white hole singularity. So all these things. Okay, and the space-time cannot be extended past these singularities, so it ends there. So these don't have asymptotic regions, while these do. Okay, good. People like to ask the question, what about nature? Do white holes arise in nature? And that's an interesting thing. I'm making a bit scattered comments without trying to connect all of them up just now, but I think they're all important in their own way. So let's ask what happens if a black hole forms in a physical process. So suppose we have actually a collapsing shell which is spherically symmetric. So collapsing spherical shell. Then let's first ask that question in Schwarzschild coordinates, where this is R and this is T. Okay. So now that shell is going to be like this. It's going to have a radius and this is matter inside. And the fact that it's collapsing is the fact that this is going in towards R equals 0. But now there is a value 2gm, and at some point this crosses that value. Okay, and what happens is that you continue this till it reaches here at R equals 0, and after that you have the R equals 0 singularity. So this is the picture, and now what can we say? Now a horizon develops exactly here. And so after that, this in these coordinates, this is the horizon, this is the interior, that's the exterior. Okay, but there's no sign in this diagram of any white hole or any region 4. But we can see already in this diagram region 1 which is here and 2 which is there. So that actually means, this is in Schwarzschild coordinates, this actually means that in Kruskal coordinates there is a reduction which has only regions 1 and 2 and no 3 and 4. In that case, this how do we say? So this will be the exterior, this will be the interior, but there has to be a spherical shell. Otherwise, we'll actually hit this, and this would be a mystery if we hit it, because this is a past event horizon, and there shouldn't be any such thing if I'm making the black hole by collapsing a shell. Okay, so actually the diagram has this matter covering this thing. And then it's the same thing as that but turned sort of sideways. And so you don't actually, the fact that this is absent comes from the fact that sufficiently in the past there was no black hole. It's rather challenging but very interesting fact that you can consider either a black hole such as I've drawn up there, which just has been present for all time from minus infinity till now. That's called eternal, and that's what the Kruskal diagram with 4 regions described. And this one, which is actually the collapsing spherical shell. They're quite different physics. Because in this one, there should not be a black hole if you go far in the past, because there was a shell of matter and it was outside its own Schwarzschild radius, so there was no black hole. Okay, so the only thing a particle should see is a shell that it can't go into while remaining in the vacuum space-time. There will be some other space-time inside, but we don't know what that is, and that definitely doesn't need to terminate in a horizon. It will just be some other space-time obtained by solving the Einstein equations with matter. Okay, so in this case, there's only region 1 and 2, and then you can also rewrite this in a more familiar way in the what is called Penrose diagram. And in the Penrose diagram, well, I'll leave it to you as an exercise. But so we have to always be clear, it's the same thing basically, but in the Penrose diagram, R equals 0 is vertical and you have to block it by this shell. The main point here is that there's no, there are two different things. There's the 1 and 2, which is the collapsing shell black hole, and then there's the region 1, 2, 3, 4, which is eternal. And we can ask questions about each of them separately, which might have different answers. Okay. Now, this actually process shows that there is no need to form a white hole, and actually it's not clear what you should do to form a white hole. The white hole should have already been there at time minus infinity. Okay, and then it is something which keeps giving off everything from inside and can't take anything into it. Okay. So this argument of collapsing shell suggests that there doesn't always have to be a white hole. But of course you can do something mathematically. You can first create a black hole by collapsing a spherical shell, and then you can say once it's created, I'm going to maximally extend my space-time to have all the four regions. Okay, so in that way they are sort of related. Good. Good. Now one question you may ask is Schwarzschild space-time, and we haven't asked this question yet, is it globally hyperbolic? We spent a lot of time discussing global hyperbolicity, and now we can actually look at it. And obviously the best way to do it is in the Kruskal coordinates, which cover the whole thing. But you might also be able to ask that, you can also ask that question just in the spherical shell collapsing. Is that space-time, which is actually time dependent in the beginning as the shell collapses and then tends toward the time independent static Schwarzschild solution, is that globally hyperbolic? And the answer is yes. So max extended. Yes, it is. And also the collapsing shell, again it is. And let's see why. So the Kruskal diagram, V, U. Now we have to draw a Cauchy hypersurface. And okay, and we have these things. And pretty much anything will do. For example, let's consider this one. This is just t equals 0, and let's call it sigma, and see if it really is a sigma, which is that anything to the future of it, if I have any point to the future, there is a past directed ray which will intersect it, has to intersect it. And from the past, all future directed rays have to intersect it. So that's the definition of globally hyperbolic. And well, that's the same statement as saying that let's consider first the right half of this. Okay, what is the future? The future is everything bounded by this and everything above, bounded only by that. But of course, this is exactly what the causal future should be, even if there wasn't a black hole, because you couldn't have gone there by a causal curve. It's outside the light cone. Light cones are all at 45 degrees, so this analysis is easy. So of course you know that from here, outside here, from this Cauchy surface, you could go that way and you would reach sky plus, or you could go that way and you would go in the black hole. Both are causal curves. You can therefore follow both of them back. You will get a past directed causal curve. You don't have a future directed causal curve coming out, but certainly the reverse of a future directed curve going in is a past directed curve coming out. That's there. And you can pick any point you like, both in region 1 and 2. And when you continue it back in a causal way, it has no choice but to hit sigma. Same thing can be done starting in region 3 and 1 in the past of this line, and any future directed causal curve from any point, whether inside the white hole region or outside it, has to cut the Cauchy surface, and so it's a Cauchy surface. Has to cut the surface sigma, and so it's a Cauchy surface. We don't have to ask the question whether any rays from region 4 will cut it, because there are no causal curves there which will cut this part. But by symmetry, any causal curve which is starting or ending here is going to cut the rest of it. So it has to, so the Cauchy surface has to go through the whole thing. We can't just stop here. It has to go from one end to the other. Okay. In the Penrose diagram version, there's the space-time has this nice hexagonal look. The singularities become straight. If you remember, there was that tan u plus v thing, so u plus v was constant, and that was r, so that was t, so there t equals constant, And here we have this thing, this is scribe plus, this is another scribe plus, this is I0, this is another one, and so on. But now I can still draw a Cauchy surface, and of course these lines are there, these are the constant u and v lines, and I can still draw my Cauchy surface like this, which goes from this I0 to that I0, spatial infinity. And of course these are just one example, but nothing really is going to go wrong if I wiggle this surface, as long as it remains achronal. It's supposed to be achronal to be Cauchy. And in this diagram I can do the same. I can just wiggle it and raise it and lower it. It shouldn't go through the singularity, but otherwise it's a good Cauchy surface. So I have plenty of Cauchy surfaces, and they'll follow all the rules that I laid out several lectures back. For example, each of these is topologically equivalent to the next one, they foliate the space and everything. So it's a very good space-time. Okay. Now what about if I had the collapsing shell type of space-time? Then this would vanish, but you can see trivially that almost nothing has changed, because anyway what's left is the region that was accessible to this part of the Cauchy surface, and now the new Cauchy surface has to end there. That's all. So in that one, this also goes from the Penrose diagram, and we just draw our Cauchy surface like this. Okay, it's a little different. In the past, if I had a collapsing shell, then I should really have this, and my shell sort of collapses because there's no yeah, how to say it? I guess this also is not right. I'm very bad at drawing. The shell collapses sort of by going in there. So, but there is an r equals 0 region in the past. It just disappears at some point. Anyway, whatever it is, it's globally hyperbolic. That's what we care about. This may not be true for all black hole spacetimes, but certainly is true for the Schwarzschild spacetime. So any questions about that? Again, I have a panic if I switched on the video, but I guess you people can always see that I did it.
We can wiggle the Cauchy hypersurface, but it has to start from I0.
Yes, yeah. In the Penrose diagram, has to start from I0.
So we can
you see in this regular space-time diagram, what is happening is I0, space-like infinity, is actually all the points at space-like infinity scrunched together into one point. So here you could raise it, for example, the whole thing like that, and it could end in at infinity at some other fixed time, not necessarily 0. But once we do the conformal compactification, they'll all bend and reach. They're all supposed to be space-like, so they'll all bend and reach I0 somehow. Okay. One more. So we ticked off a number of things, features of Schwarzschild, which we could understand best in crystal coordinates. Now there's one more, which is the killing vector. This killing vector is pretty mysterious. Of course, it was always del by del t in Schwarzschild coordinates because that factor 1 minus 2 gm by r didn't depend on t. That's the reason t was a killing vector, and that's very simple. The problem is it seemed to abruptly change its character on the other side of the horizon. And then in the Eddington-Finkelstein, we could sort of see that, but t was no longer a coordinate. Now v was the coordinate along with r, and r was null. So it's all a little confusing. Now with Kruskal, all the kind of the normality returns. So first of all, what is the effect? So this generates the translation t goes to t plus some constant c. So when I do this, what happens, and of course r remains fixed. Since r remains fixed, r star also remains fixed, and that means u and v undergo the same transformation as t. So once I go to Eddington-Finkelstein, then u goes to u plus c, v goes to v plus c, And with this, I can ask what happens to capital U, and of course it gets scaled. So it goes to e to the minus c by 4 gm u, and v goes to e to the c by 4 gm v. Now, in any system of null coordinates, if I scale one of them up and scale the other one down, then I preserve their product, and that's exactly a Lorentz transformation or a boost. So this is a boost on the crystal space-time, and we can easily write down a formula for this explicitly. So the Killing vector now as a vector field is 1 by 4 gm u del by del u minus v del by del v. Okay, good. And what is its norm? Since and now it's defined everywhere, all 4 regions, nothing wrong with it anywhere. And we can ask what is its norm, and so we calculate k squared, and we find that it's minus 1 minus 2 gm by r. Conveniently, the norm of this Killing vector is given as a simple function of r, which itself is a complicated function of u and v. And with this, we can see that it's time-like in 1 and 4, which are both outside the horizon, and it's space-like in 2 and 3. Okay, so that's an easy one. We can also ask what it looks like in r comma t, that capital T and r coordinates, which we got by taking u plus and minus v. So k is also equal to 1 by 4 gm r del by del t plus t del by del r. And you may recognize this as a Lorentz transformation. If this was a minus, it would be a rotation. If t was renamed as some other space coordinate, then x del y minus y del x is a rotation in space, but you change minus to plus, then you get a Lorentz boost in one space, one time. And so this is a boost, as expected. Okay, but we still haven't settled the question of which way it points. And oh yeah, so okay, so it's these things, and of course it's null on horizons, all horizons. There are 4 horizons, in fact. Well, you could say there are 4 sections of the horizon. So this we call future event horizon and past event horizon for region 1. But remember, region 4 is an independent universe, and it has its own future and past horizon, and k is null on all of them. Okay. Now, what about the direction of k? We would like to draw it on the physical coordinates, and what we can say is that 1 is our most familiar region, and surely very far away in 1 it must point up, okay, because the light cone is up and this is time-like, and it's a convention. We have to choose we said that it's time orientable, we have to choose the orientation, so we'll say that it points to the future here, okay. But now we can follow this in either UV or RT coordinates, and what we'll see, which is actually very similar to Rindler space-time, for the obvious reason that these are like this is like an accelerate, this is like a boost, if you like. So it's boosted coordinates. So k, the time-like Killing vector, starts to bend like this, and once it comes on this horizon, then k is null and it points this way. Okay, you can see that by continuous motion it can If it's pointing up, it's still pointing up here, except it's null. Okay. We can also see that by the formula, because we had 1 by 4 gm u del by del u minus v del by del v, and on this u is 0, this axis is u equals 0, this goes away, and this is a uniform scaling of the v coordinate. X d by dx is a scaling. So and it simply points that way. It just takes every point here to some multiple of the original point. Keeping the origin fixed, as we will see, that's important. Notice, by the way, that at the origin the Killing vector vanishes. That's one more important property, and it's really important. So k vanishes at u equals v equals 0, and well, that's visible from this formula. Just set u and v to 0, then k vanishes. Okay, and by the way, that's not a point, there's still a sphere over here. So in fact, these two null hypersurfaces are intersecting over a space-like surface, that's a sphere. You could ask, what's the radius of that sphere? What is it? It should be clear from just continuity. What is the radius there? Exactly there. Well, all along this is a horizon, so the sphere is 2 gm. All along this also horizon 2 gm, therefore the sphere has radius 2 gm there. Okay. In general, it has less radius, it becomes smaller in these regions until at the singularity it shrinks to 0. Okay. You remember that when we first introduced null hypersurfaces, we had them intersecting over two-dimensional space-like surfaces. And here is an example in a real-life solution that is not Minkowski, in fact non-trivial and different, but still has the same property, that there are two null surfaces and they intersect on a sphere. Okay, good. Now we've seen that it's null here. Now what's it going to do here? Here it's got to be space-like. That means it's either pointing to the right or the left. It's pretty obvious from this diagram that by continuity it will go into this, pointing to the right. Then we bring it to this horizon, and now by continuity you see it's got to be null, but it's pointing that way. And actually you can see that from the fact that what I have drawn is not u del u by minus v del v, it's actually minus of that. I mean, Killing vector you can always put a sign, but for it to be pointing up here, so that it's pointing this way here, the v del by del v needs to be positive. Okay, I could have just started with that definition. If that's positive, then u del u here is negative, because u is positive, and so there has to be a minus sign for it to point this way, and it's there. So we can clearly see the null ones are very trivial, because anytime I put u or v to 0, I know which way the remaining thing points by asking for the sign of the other one. So here v is 0 and u is positive, therefore minus u del by del u points that way. Therefore over here it's going to point down. Okay, and now when it reaches here, it's again going to be null, but now it's going to point that way. And let's check that this is correct. Now we are at u equals 0, but v is negative. If v is negative, then we have one sign, two signs, and a third sign from v being negative. So it is a negative sign, so it actually points down. And then finally you can easily complete the diagram by saying, well, here it must be pointing to the left, and then on this it points this way, and by continuity it comes back to this one. So it's future time oriented here, past time oriented here, and space like here, but in opposite directions, and null on all the four segments of on all the four horizons. Good. Okay. So we made a fair amount of progress in understanding the space-time. in using the critical coordinates. There's one last thing to discuss, which is what the hell is region 4. And well, in some deep sense, it's really a mystery for the following reason. So there are two properties. One, 4 is causally disconnected from 1, that's obvious. There is no way to get from region 4, from or to region 4, between region 4 and region 1, because they are space-like to each other. So any curve that tried to go from here to here or here to here would have to be space-like and can't be causal. So that's nice. That would tempt us to say that, well, this really doesn't exist and we can forget it. Okay. There's a problem though, which is that a causal curve from here can certainly go here into region 2, and a causal curve from here can go here also, and the two can meet over here. So if I have an observer here and an observer here, if they both jump into the black hole in a carefully timed way, they can meet inside and describe how life was in their respective. Yeah, we had a small storage issue. So I was saying that if you have observers going into region 2 from 1 and 4, they can both meet here and they can talk about the past that they experienced while going in spite of the fact that these two are causally disconnected. But of course, as long as we are still in classical physics, they can talk as much as they like, but they can't tell the person in region 1 about region 4 or other way around. They can just tell each other while they are drifting into the singularity and about to die. So that's how it is. You could also realize that from region 3, if there is really a white hole, it can be emitting cheerfully into both regions 1 and 4. So region 4 remains in that way slightly mysterious. There is one thing one can say, one more thing one can say about it, which is to ingest some language. And that language goes by the name of wormhole or Einstein-Rosen bridge. So let's give a definition. A wormhole, this term was invented, I think, by John Wheeler, who also popularized the term black hole. Not sure if I don't think he invented that one. Is a compact region of space-time connecting different universes with different asymptotic regions. And 1 and 4 are precisely different universes with different asymptotic regions. Now it's important to be careful about terminology. When we say connecting, we are just talking about topological connectedness. We are not saying there's anything causal about that connection. And in fact, if the connection was causal, then we can actually go from one to the other, but we just argued that we can't. If it was, then we would call it a traversable wormhole, because we could travel through it. And there are attempts to make traversable wormhole models with traversable wormholes. They typically tend to violate some or other condition, because this is a vacuum solution, but you want to have something interesting, you may put some matter, but then your matter has to satisfy some weak energy or strong energy condition, and then it might violate. If it violates all that, then probably you can get these. but they're seen as somewhat exotic. Again, they're somewhat, they are the subject of discussion. Yeah, but still we call it a wormhole, and the idea is that we can have slices. Either the simplest slice is this, but actually we can have plenty of slices. This one, this one, this one. All of them go from region 1 to region 4. And what they do is they pass through a region where there's a sphere which is sort of shrinking. Okay? And that's because as here r is greater than 2 gm, here also r is greater than 2 gm, but r is decreasing, is exactly equal to 2 gm here and here. So it must be at some minimum point in the middle. So in between, so here wherever we are, wherever we cross, depending on which line it is, we'll encounter a sphere which has some small size compared with the size of that same sphere outside and asymptotically. And in particular, the maximum size of the wormhole is actually 2 gm, and if I go there. If I go through this point, as I told you, it's on both horizons, so r is 2 gm. But if I'm here, since it's decreasing and increasing, and here I've gone closer to the singularity where r is 0, so here r is less than 2 gm. That's important. So it's obvious also if I cross, I know I've crossed into a region of less than 2 gm. But then if I cross out, it started increasing again. So on the exact midpoint line is where you will find your minimum r, whatever it is. And you can make it as small as you like by taking your wormhole, go down as close as you like to a singularity or up. And you can make it only as large as 2 gm and never larger than that. Okay. So that's the wormhole story. And now we'll embark on. So that's been a lot of physical discussion, maybe for a change in this course. And I hope there's some insight came out of it into what these 4 regions look like. Yes, please.
What is the definition of universe?
Universe. I forgot, thank you, that reminded me something. It's a little arbitrary because in fact, you can even have a wormhole which connects, you can even have a wormhole of one connected space-time with 2 asymptotic boundaries. That also is a wormhole. So it's a very loose thing. I mean, universe is what this appears to be. Universe looks like they're completely disjoint and not connected causally. But what could happen is you might have one space-time which is also has a causal path. And somehow, wormhole, I think in science fiction, the idea is that I want to get somewhere, I have to wait a million years, but if I find the right corner of space-time, then in 5 minutes I can be there, the same place. Because space-time has somehow cleverly curved and its causal structure is such that actually the others, it's like you have these sheeted, people draw these sheeted surfaces and put a little tube through it and all that. So yeah, there's not a very good meaning of universe here. For this purpose, it's just whatever is near an whatever is connected to an asymptotic boundary is a universe. But it's
Sorry, I did not exactly understand what is the compact region here, which is connected.
the 2 sphere. So the wormhole is this line, but the line is a hypersurface, right? So these simple lines I've drawn are t equals constant lines, so their coordinates are r, capital R, theta and phi.
Yes.
But now capital R is going this way, so and at each fixed capital R there's a theta and phi, so there's a 2 sphere. So the wormhole is a 2 plus 1, it's a space-like thing, it's a 3-dimensional, at least in this case, it's a 3 Euclidean dimensional thing, and every point of it so you can say one coordinate is the one that goes from and to the other universe, so that is R. Every point on that wormhole is a 2 sphere. That's the 2 sphere. It's the constant R2 sphere at the fixed t, which anyway was fixed in order to find a wormhole. I mean, of course, it doesn't have to be fixed t and constant r. These are the simple ones that I can draw with horizontal lines, but you get the idea. There's always going to be a two sphere of radius theta and phi.
No, but I mean, it is not compact because this R is.
No, the region that it's passing through, that means it's so imagine that R is, so just think of R as the coordinate which tells me where I am, and at each place where I am, I ask what is my space around me in that wormhole. That's a two sphere. So what I say, just words, is that I start here at a particular R and I have a two sphere. Then I follow my two sphere and it's shrinking and then expanding, and therefore I call this a wormhole. So I pass through it's a compact region, and it is sort of small in some sense, smaller than what it would be at asymptotic infinity. Because in fact, asymptotically, that two sphere is just the two sphere of 3D space-time, and so it's actually just growing without limit. It just grows as r goes to infinity, and r is the radius of that sphere. It just grows. But then from that huge two sphere, I go in and I find it shrinking till it reaches an absolute minimum, and then it expands again. So that's the wormholeness of it. Okay, good. Now we'll start a topic which we can't finish today, and therefore it will have to be finished next week. I'm sure it can be finished next Tuesday, but it's extremely important. I could have postponed it, but somehow, because when we discuss singularity theorems anyway, it would have to come in. But we are right at the place where we should be discussing this. So let's introduce the ideas. We've already, I think, have I already introduced what's a Killing horizon? It's a very simple thing, even, you know, okay. Now in my notes it has shown up in much earlier. I'll send some revised ones. But basically, so, okay, the discussion is this and bifurcation surfaces. And some of this, at least the obvious geometric part, we can do now without much work. And then there'll be some algebraic part which is quite tedious, involving manipulation of some Killing vectors and so on, and that we may have to do next time. So, definition. So first of all, okay, Killing horizon is a null hypersurface. That you know what it is. If you remember, the null hypersurface is defined by having a vector field which is normal to it and lies in it because it's null. So the vector field normal to it is null. That's enough to say it's a null hypersurface. But since it's null, it also lies in that surface. Okay, and such that the normal, the null normal V is a Killing vector. So it's an isometry direction of the manifold. Manifold or some region of the manifold. So it's nothing, it's just the standard null hypersurface, but the normal V is not just any old vector field, any old null vector field, it's also Killing vector. Okay, the Killing vector doesn't have to be null elsewhere other than on the null hypersurface. So if I have a null hypersurface, then I have a Killing vector which is parallel to it, but elsewhere the Killing vector can do anything it wants smoothly, but it should be null on this, and once it's null along this surface, it will be the normal to the surface. This works both ways. If something is null and lying in a surface, it's also normal to that surface. Of course, as long as it's normal to the space-like directions of the surface. So since if we take this to be since here we are taking, we can take three coordinates, one of which is this one and the other two are say theta and phi. I hope you recognize that this is nothing but a piece of the Kruskal diagram we've already discussed. Okay, so we can immediately see that, so example of a killing horizon is the future and past event horizon of Schwarzschild. These are examples. To test that, we simply first argue that they are null hypersurfaces. We've done that because they are u equals 0 or v equals 0, both are null hypersurfaces. Then we ask what is the normal on it, which is along it, and we realize that it is nothing but our friend the killing vector, which is defined everywhere in Schwarzschild's extended Schwarzschild spacetime, and which is null exactly on it. So it's a killing horizon. It's just we are restating things we already knew. We already knew they are null hypersurfaces, and we already knew that the killing vector d by dt turns null on them. And that's enough to say that they are killing horizons. But these are examples. Now, what is our point? Our point is to make theorems about general event horizons and without necessarily knowing what black hole solution we are making the theorem about. I think I said some of this towards the early part of this course, that the sort of thinking that pervaded these three people, Raychaudhuri, Penrose and Hawking, in that order in time, was that by their time, if you were very clever enough to read all the past literature, you realized that a lot was known about very, very simple solutions to Einstein equations, one being Schwarzschild and one being the Friedmann-Robertson-Walker expanding universe. Just utterly simple, almost no parameters and so on, and still very profound with a lot of structure in spite of that. But the question that was live at that time was, how much can we trust these simple solutions to tell us stuff about the real world? And that will repeatedly, now from now to the end of this course, that will repeatedly be the question. We have an example, lovely. We have a killing horizon, lovely. But what are we going to learn about generic black holes which are not Schwarzschild, which we may not know how to find, or which might be Kerr and we may not have time to sit and plow through all that solution? What is the general rule about that? So that's why we make an abstract definition of a killing horizon. And there's a theorem. Okay, so first killing horizon, but that's not all. There's a second definition I need, and then I'll give you some theorem. So this is one definition. Another definition, which actually does not involve killing horizons, strangely, is a bifurcate killing horizon. This is a slightly more, but it's also something you have seen. Let me write it, and I'll explain why I said it doesn't involve killing horizons. Is a pair of null hypersurfaces, so there are two now. That intersect over a space-like surface S. It's obvious that in 4 dimensions, the null hypersurfaces are dimension 3 and they intersect over a 2-dimensional space-like surface, such that, and this is the killing part, such that some killing vector in M vanishes on S. So, first of all, the killing horizon is everything like that. There are 2 null hypersurfaces, and here is the S, which is shown as a point, but it's a two-sphere, as we have discussed repeatedly. Now, in the Schwarzschild example, we had a little more structure than this theorem, this definition requires, but it is an illustration of this. So in this example, this was itself a killing horizon, and this was another killing horizon. Okay, so both of them had some null vector on them, which was an isometry. Okay. Now, when you come here, the isometry runs into a problem. We've seen that actually with K, because K is supposed to go like this here, and like this here, and like this here, and like this here. And what on earth is it supposed to do at that point? By continuity, it looks like it doesn't have many choices what to do. Have I drawn it right? I think I've drawn it wrong. This. So this and this are opposite directions. So obviously it must vanish here. This and this are opposite directions. So again it should vanish here. Okay. So basically it vanishes at this point. So in that case we have two killing horizons which intersect, and together the pair of them is a bifurcate killing horizon. But the more general definition only requires that there is a killing vector. It need not be the null normal of either of these null hypersurfaces, but it vanishes there. That's the important thing. Okay. Real, by the way, Harvey-Real does require in the definition, he says a pair of killing horizons that intersect over a surface. If they are already killing horizons, then when they intersect, the killing vector will go to 0 at the intersection. But the more general definition appears to be only that we require it to vanish, killing vectors, one killing vector to vanish there, which need not be the null normal of both of the horizons. Okay, and also S has a name. This is called the bifurcation surface. So the intuition, and I again emphasize, intuition is only got from Schwarzschild solution, so we can't make theorems out of that intuition. But the intuition is that there's a past, that the past and future null horizons intersect on a bifurcation surface. Okay. Now, there's a theorem which I'll state, but we'll actually maybe never going to prove it, but we will try to motivate it. I'll see how much of a proof I can make up by next time. So the theorem, which is due to Hawking, says that with some conditions, basically it says that every event horizon is a killing horizon. That's what it says. And in the Schwarzschild case, it's clear because we first found the event horizon, and of course then we defined killing horizon, and it satisfies bifurcate killing horizon, and it satisfies that. But he wants to say it more generally. So in an asymptotically flat, so there are a couple of conditions. Stationary, not necessarily static. And we use the word analytically continued, which is this statement that it is maximally been extended. Because as you can see, it's less clear for a, it's not true for a collapsing shell, because that doesn't have a bifurcation. So there is no past event horizon. So analytically continued space-time. Vacuum. Vacuum black hole space-time. So it needs all these things, but as you can see, except for stationary, Everything else is pretty much general. I mean, it's, you know, there's some it doesn't apply to ADS black holes, for example, but it's pretty general for flat space-time. And we'll see that stationary is also something quite important. So what's the last line of the theorem? The event horizon is event horizon, which is actually the union of all event horizons, is a bifurcate Killing horizon. And if you want me to just say in words, it basically says that this X structure and 1, 2, 3, 4 regions structure is general under these conditions. It's not only Schwarzschild which is like that. Because in fact, when you have a bifurcate Killing horizon, there are 4 things going out of that bifurcation surface, the sphere. There's one null hypersurface going this way in the future, this one in the future, then that in the past, and that in the past. It's a bit confusing because even in the mathematical literature, they say 4 directions out from a 2 sphere. That's a little bit annoying because there can only be 2 directions, but now they are counting future and past separately. And the reason is because of the bifurcation, these 4 semi-infinite directions actually divide space-time into 4 regions. That is the key. That's why 4 is the correct way to count. Because though you're counting semi-infinite directions, you can't get from the past event horizon to a future event horizon without passing through this bifurcation surface. Good. So, yeah, I actually want to end now. So I think this is a good point to end, a little bit early today. And we will continue on Tuesday next week.